Hello, and thank you for joining us. On behalf of VDURA and Carahsoft, I would like to welcome you to our VDURA webinar, Flash Forward, Smarter Storage at Scale Without the Trade-Offs. And at this time, I would like to introduce our speakers for today. David White, Federal Account Executive at VDURA, Steve Leibowitz, Senior Solutions Engineer at VDURA. David and Steve, the floor is all yours.
Thank you, Eli. I'm going to go ahead and share my screen here.
Yes.
Yep. Thanks, Steve. All right, welcome everyone, and thank you to Carahsoft for hosting this webinar today. I'm going to begin with some introductions of myself and Steve. My name is David. I'm an account executive here on the federal team at VDURA. I joined back in November 2023 when we were still Panasys, and I'll get into that a little bit on the next slide. Previous to this, I've held pre and post sales roles at big data companies and AI companies, notably DataRobot and Starburst Data. And then in between those two roles, I spent a few years working in IT project management with Northrop Grumman at the Department of Treasury. So a wide range of experience. I've gotten to kind of be in the federal IT space, working as a project manager there, and then also work kind of in the sales role, providing services, software and hardware to the federal government. And now I'm going to pass it on to Steve and let him introduce himself.
Good morning, everyone. My name is Stephen Lebowitz. I am a senior solution engineer at VDURA, focusing on the federal marketplace. I've been doing HPC and AI for roughly 30 years or so. I started working in this area in the early to mid 90s with the Department of Defense HPC modernization program. And I've worked across a number of industries, spending the bulk of that in DoD and intelligence. I held a variety of technical roles at a long career at IBM, and then also worked for several other smaller companies, mostly focusing on HPC and cluster design. David?
Thank you, Steve. Before we dive into the technical details today, I wanted to give folks some context about VDURA and why we're uniquely positioned to address today's federal storage challenges. As I mentioned before, we were previously Panasys. That name change happened around May last year. But VDURA has been at the forefront of parallel NAS and high-performance storage for over 2 decades. We've been powering some of the world's most demanding HPC research environments, from national labs to defense contractors, with our PanFS parallel file system technology. But here's what's changed dramatically over the last 2 years. We've transformed from being purely an HPC company to becoming an AI and data platform company. This wasn't just a messaging shift, it's a fundamental reimagining of how we architect, deploy, and support storage systems. So why did we make this pivot? Because frankly, our government and all of our other customers are facing a new reality. AI workloads aren't just another application running on existing infrastructure. They were becoming mission critical. They demanded entirely different performance characteristics and required storage that could keep GPUs fed without creating any bottlenecks. So we rebuilt our approach. The V5000 platform we'll discuss today represents that evolution. It's purpose-built for AI workloads while maintaining that enterprise-grade durability and simplicity that federal environments demand. This transformation also aligns perfectly with what we are seeing in the current federal landscape, the need for proven commercially available solutions that deliver measurable efficiency gains rather than custom-built systems that require extensive integration and management overhead. So, Steve, that sets the stage pretty much. Now let's talk about what's driving the urgency we're seeing from federal customers. And we'll kick things off first with a little context, right? So, Steve, from your perspective, what's changed over the last 12 to 18 months in how federal agencies are approaching infrastructure, especially with AI and data workloads becoming mission critical?
Thank you, David. So 12 to 18 months, I think, is what we've seen mostly in the federal space, but it's really following what we've seen happen in the commercial sector for the last, say, 5 or 6 years, with an emphasis more on machine learning and AI and the rise of large language models. When we think about the change in computing resources that have taken place over this time, and we're starting to see happen inside federal agencies. On the left, we see a more traditional HPC-centric infrastructure, primarily CPU focused with a high-speed network, uh, some long-running jobs that require very write-intensive checkpointing, but mostly sequential read and write workloads. A job will start, it will read in a data set or data sets, compute for some period of time, and then write out a result at the end of that. The files in these kinds of applications tend to be fairly large, 100 gigabyte or more, and you have millions of files in your file system. When we think about what happens in the AI and ML space, we see a shift now to primarily a GPU-focused compute infrastructure, similar high-speed network, either InfiniBand or high-speed Ethernet, so 100 gigabyte or greater. But now we have both a write and read intensive set of workloads, especially doing model training for machine learning. We have a mix of sequential and random IOs that are taking place. And now we have a much larger range of file sizes, ranging from still gigabytes or even, some cases, terabytes of data down to very tiny files, K, 64K, 16K kinds of things. And now we're seeing not just millions of files, but many billions of files that need to be within a common namespace. But the biggest difference in all of this is the users themselves. In traditional HPC, a user would not be able to run the application on their local workstation. They would be able to build or generate input data sets, and they could check to make sure that they would start, but they could not effectively run them because they would take too long to reach completion. And so they would have to do the bulk of their work on the common HPC cluster that everybody would use and go through the job scheduler. With AI and ML models, we can actually do some of that work on our local workstation. So we can test the training, we can test the inference workloads. Even though they won't be fast, we can still see results. So what we get now are different kinds of users with different kinds of workflows and how they deploy them. And then the AI ML users, once they get their models to a point where they think they're workable, they upload them to the larger cluster and they run much larger data sets. And that's where they get to spend weeks, if not, a month or more running a model if it's a training session. Or if it's an inference model, something that just runs all of the time and constantly updates with new information for its training data set so that it can keep up with the things that are coming along. But you get this real fundamental difference in the way the users behave and the kinds of things they expect back from the clusters and the storage environment itself. David?
Thanks, Steve. So going back to what I mentioned about urgency earlier, what's driving that urgency around legacy modernization? Is it purely about performance, or are there other pressures in the mix? And then additionally, when we use the phrase trade-offs, what do we mean by that? And can you unpack what that really looks like for federal IT teams?
So we do see some urgency around the modernization of infrastructure. In the past several years, there has been a huge drive towards NVMe or flash storage systems. Companies like VAST or Weka have made great inroads in the last 5-6 years in promoting the performance of all flash systems. The difficulty here is that these things can be challenging to manage, and because of their cost, you can't afford as much flash as you could in more traditional bulk storage, HDD-driven storage systems, or even things like S3 buckets that we would, rent from Amazon or some of the other hyperscalers. The difficulty here is that while object stores and bulk data storage is much less expensive, it does not perform necessarily at the same speed. But if I want to run on high performance flash and then keep a lot of data on bulk storage, I have to have a way to move that data back between those two storage tiers. And this increases the complexity and administrative burdens that are placed on the IT teams. And when we think about the cost of a program, the vast bulk of the cost of a program is in labor. And if we want to show value, we need to make sure that we're emphasizing tasks that are moving the mission forward, whatever that mission may be, as opposed to spending time maintaining and managing the IT infrastructure that supports that mission, because it does in fact support the mission. It is not the mission. David?
Thanks, Steve. No, great answer. And shifting gears now, let's start talking about the solution, right? So for folks who aren't familiar with our V5000 platform specifically, can you give us a high-level overview of what this system is and then why it was built with federal requirements in mind?
So let me start at the very top of this chart. You see this concept called a global namespace. And here we have an area in which, think of a file system. Again, we all know them. It's a tree of data with directories and files within the directories and subdirectories going down many, many levels. And as we keep data over time, the complexity of that structure only increases. So by having this global namespace and potentially even having just a single mount point that I can extend to my clients, I can make this large set of data available to all of my users. In the middle there, just below the global namespace, we see the clients themselves. And this is here to represent really the diversity in the types of clients that we're going to be able to support. Natively, we have what we call direct flow, which is our own parallel file system client. This gives you very high performance parallel access, meaning that we can support multiple simultaneous read and write transactions for an IO going to multiple elements in the storage array that are at the bottom of that chart. And so that's how we get really great performance across the whole system. And many clients may be using direct flow simultaneously, as may clients using other protocols such as S3, NFS, or SMB, otherwise known as FIFS, to support, say, Windows workloads. Now, all of this is connected, you can see by that blue box in the middle, which is a commodity Ethernet or InfiniBand network fabric. And that network fabric will be, something that is already provided in your data center by your IT network team. And they will give you whatever speed, you've contracted for from that team. That could be 100 gigabit InfiniBand or Ethernet, 200 gigabit InfiniBand or Ethernet. And today we're seeing InfiniBand in the 400 gigabit and soon 800 gigabit at the client speed. Right now it's at the switch level, but not fully at the client speed. Now, at the bottom of this chart, you see an array of what we refer to as storage nodes. And these storage nodes fall into two classes. On the right, you see the storage nodes with the small red drive objects arrayed below them. Those are our flash storage nodes. They contain only NVMe flash storage and respond very, very quickly, as we would expect, to IO requests. On the left, you see similar nodes that have flash storage, but also have a capacity expansion JBOD below them, and that JBOD contains HDDs. In our case, we support two different size JBOD drawers. One is a 78 drive unit and one is a 108 drive unit. So that gives you some idea for the density of the storage that we can provide with a single storage server is not just what's contained in that flash, but also in the capacity expansion attached immediately below it. Now, that's where all the user data is kept. But we also have to think about the metadata. And this is the information about the information that's stored in the system. So we have this concept called an inode, which is really information about a file or a directory. It tells us not just what's going to be in that file, but the length of the file, the time it was created, the time it was modified, as well as where the data blocks are located within the storage environment to retrieve the information of that file. And those data blocks are numbered so that we know where the beginning is, where the middle is, and where the end is. Now, the storage nodes do not actually answer requests about the metadata itself. They store the metadata, but director nodes on the left side of the chart actually absorb that metadata and then provide high-speed access to that by keeping it in memory in a very high-performance key value store. So anytime you ask to open a file or to write to a file, or just to get information about a file or directory, what the contents are, for example, that request will go to a director node, which will then respond, having had that information loaded into its key value store in memory. How does that work, David?
I think that's a great overview. Thank you, Steve. I wanted to shift gears a little bit and go back about something we've already talked about, right? AI workloads. I wanted to dig a little bit deeper into this. So can you talk about how V5000 architecture supports real-time model loading, checkpoints, and inference, especially at the scale we're seeing in C2ISR, cybersecurity, and research applications?
So we talked a little bit earlier about how in traditional HPC workloads, you have a lot of sequential read, compute, and write kinds of jobs. AI and ML have a little bit of similarity, but there's a number of really interesting differences here. So on the left side of this chart, you see that first green section below the line, which indicates that it's a write operation. That's really the ingest of data for the model itself. That's where we're absorbing information that we want to keep and then be able to use later to either satisfy a query or to train the model itself. Then we see a large read input, which is how we sort of stage information into an ML training session, for example, or loading a model into a GPU. And then you see in the gold area, this is when either the model training or the inference model is executing. And you see a lot of read and a little bit of write going on all throughout that process, because we have to keep, things in place and make sure that we're keeping the information that we want to keep. In long running model training, we do want to stop every once in a while and actually write out a checkpoint of where we are in this process. If I have a model that's going to take me 6 weeks to train, and I don't checkpoint it once in a great while, we know that in large HPC and AI clusters, things are going to fail. A node is going to go offline, the job is going to stop for some reason or another, and we're going to have to restart it if it's a really long running job. So these checkpoints become important because they allow us to go back to the last known good place where we had data that we could continue from. And if I checkpoint a model after, say, every few hours, but I'm running for 6 weeks and at 2 weeks, everything stops, I don't want to go back to zero and waste all of that 2 weeks that I just spent, because GPUs are really expensive. And I don't want to waste the investment that has been put into those resources. So we go through this a number of times. And then when we look at what happens farther to the right, this is more, say, an inference style workload, where we're primarily reading data from the data set, but then occasionally we write something back out. But really, most of the I/O is occurring on the read side and then sending transactions back out to the users who requested something to be processed in the first place. David?
Thanks, Steve. I like to liken the checkpoints to video games back in the day where you hit save, but the processors weren't great at the time, so the game would pause and you'd have a little spinning disc, and now you can't play the game that you bought, right? When you buy those GPUs, you want to be able to get the most out of the GPUs and get the most value out of them. So one thing I hear consistently from federal buyers, and this aligns with the current efficiency focus, is concern over operational overhead. Storage can be fast, but if it requires a team of specialists to manage, it's a non-starter. What are we doing differently when it comes to manageability?
That's a really great question. we often talk about availability when it comes to HPC clusters and storage clusters. And when you think about the amount of effort that goes into keeping the storage balanced, meaning that I don't have hotspots somewhere in the storage array or the storage cluster itself, or if something were to fail, what do I have to do to bring the system back to a healthy enough state that I can continue operation? And then thirdly, what happens if, is there an opportunity to lose data under certain circumstances? What this chart is intending to show you is how more traditional high performance storage systems that use a dual headed HA cluster kind of format, uh, actually lose availability as they grow in size. And they also, during a failure, even if they survive the failure, their performance drops rather dramatically in that process. The difference in the way that we operate is instead of doing RAID erasure coding at an array level, we do it at a file level across the entire cluster. This is called network-based file level erasure coding. And what that allows us to do is have a much higher tolerance for the loss of a storage element within our system, and to immediately not just recover from that failure, but to preserve a greater percentage of our performance in that process. Because we can recover faster and more easily, that also means the durability of the data that we keep is in fact higher, because we don't lose half the performance of an array when we lose a controller or a head node, because in that case, you lose effectively half of your bandwidth out of that portion of the cluster. In our case, let's say I've got 30 or 40 storage nodes. If I lose storage node 17, I've only lost 1/30th of my total performance. And I have 29 other nodes to help recover from that failure, which means it recovers more quickly and I can return to full operation virtually in minutes to hours. Now, we also introduce a concept called multi-level erasure coding. So in the traditional RAID array, we do RAID encoding, erasure coding at the storage array across the drives at a block level. Since we're doing file level erasure coding at the network level in the first tier, that is our normal method for doing this. We're now adding the ability to turn on an additional erasure coding within each storage node that is in some way similar to what is done at the legacy architectures. We will do erasure coding across the storage node drives within that, within the file system contained within that storage node. It's still not at a block level. It's really done at an internal file system level. But what that allows us to do is increase again our survivability and availability of our data. Where before, if we would lose a disk within a storage node, the storage element within that storage node would be offline. Now, with multi-level erasure coding, we can compute the RAID values and keep running while that remediation of that failure is taken care of. And so it means we don't lose that node 17 completely. We just lose a small bit of performance, even less than a full node, but we greatly increase our data durability. In this case, we get upwards of, say, 9 nines, if you think about this. So 99 point and 7 further nines of durability of data. That's a huge improvement over what we see in other kinds of systems. Does that answer your question, David?
Yes, it does, Steve. So what I'm hearing is we're not just fast, but we also have mission critical resilience built in.
Exactly.
So shifting gears again, there are a lot of flash storage players in the market, and Steve, you mentioned them kind of early on in the hour. Vast and Weka come to mind, but when we say things like 7.2 million IOPS or 210 gigabytes per second throughput in a single rack, how are we achieving that, and why does it matter for mission critical workloads?
So we have a lot of people who come to us and say, I want to buy the fastest thing I possibly can. And we always come back and say, well, tell me why you want that. What is it you're going to do with it? What does your workload demand of you in order to meet the timelines for whatever process you're running or whatever kind of job you're computing? And often they will, have this great desire for an all-flash solution. And if you look on the left side of this chart where it says option 1, you see that 2-rack solution. That is a full all-flash 20 petabyte cluster. And you can see the throughput on here is absolutely phenomenal. 2.2 terabytes of bandwidth per second and 76.8 million IOPS. So IO operations per second. It's also 51.8 kilowatts of power, which, while it may not be as much as what the compute cluster is drawing by a long shot, from a storage perspective, that's still a fair amount of power. So when we start talking to people about what an all-flash solution would cost, they sometimes back away from that rather quickly because they know their budget isn't going to afford that. So we want to talk to them about how you can change your needs better to match what your workloads require, and then how that impacts both performance and cost. So option number 2 in the middle of those three is still a 20 petabyte solution, but now we're only 50% flash and 50% HDD. You'll notice here that the performance is roughly 50% of what the all flash was. No shock there. But we also see that the performance is roughly half again, 38.4 million IOPS. And the power is not quite half, but that's because we still have a lot of flash involved. And you look at the relative amount of the JBODs that are in there on the first rack, it's really just a little more than half a rack, and you've got nearly a full rack of flash. So the fact that the power is a bit more than 50% isn't terribly surprising there. What's really interesting here is that the cost of this solution is 35% less than an all-flash solution, roughly. Now, over to the right-hand side, still a 20 petabyte solution, but now it's only 20 petabytes of flash. You'll notice here that the throughput is 420 gigabytes per second, still a really good throughput number, and 14.4 million IOPS. And now we're down to 26.7 kilowatts. Now, when you think about this and you think about, well, what does that really mean? Now we're getting to 60% less in cost. The way our system functions, we will utilize the flash elements of storage first. So even on the nodes where we have the HDD expansions behind it, they have an amount of flash within them, and we will fill that before we start to drain it out to the HDDs underneath them. So you can have 2 sets of storage here, what we refer to as storage sets. These are differentiators in terms of where we might want to place pieces of data. And so we can have a volume that is a flash volume and a volume that is an HDD backed volume. And then you can use whichever is most appropriate for the workload in that time. And then you get to take the advantage of the reduction in cost while preserving really excellent performance. David?
Thank you, Steve.
So let's shift gears just a little bit, David. I want to ask a couple of questions. When we talk to government IT leaders, the conversation goes beyond performance. There's a real need for solutions that are procurement ready, cost transparent, and aligned with the efficiency mandates that we see coming from the administration. So what makes VDURA particularly well suited for these environments and challenges?
Thank you, Steve. So yeah, VDURA is built exactly for this environment. And first, I'd like to give a shout out to our partner, Carahsoft, right? We're available on SOUP through Carahsoft, but also on CIOCS and ITES through the rest of our partner ecosystem. And we'll be working with Carahsoft and the other partners as GSA looks to take over these contracts. But what really sets us apart is how we align with DOGE's efficiency mandates. Our platform delivers measurable ROI through our vendor consolidation. Instead of managing separate storage silos, agencies get unified namespace management. That reduces operational overhead up to 70%. And this is critical because it allows your storage administrators to instead focus on mission critical tasks rather than the administration of the infrastructure. And agencies can also leverage that 6 to 11 nines of durability you talked about previously to guarantee, or they can use that guarantee to reduce redundant backup systems. And that directly supports the cost cutting initiatives that we're seeing coming out of DOGE. Unlike legacy solutions as well that require extensive professional services, VDURA deploys with minimal consulting overhead. This is exactly what agencies need as the government moves away from traditional advisory services contracts.
Thank you. We've had a lot of discussions recently about end of fiscal year spending and Q4 timing. From a deployment standpoint, how quickly can federal customers get systems on the ground and operational, especially given the push for rapid deployment of proven solutions?
This is where VDURA really shines, Steve. Compared to traditional enterprise storage, we're talking same day deployment versus weeks or months with that legacy storage. The V5000 ships fully configured and tested. Agencies literally rack, stack, and then they're operational within a day. There's no extended professional services engagement, no lengthy integration cycles. We've had customers go from delivery to production in under 24 hours, and that's pretty remarkable. Given the current focus on rapid deployment and the pressure agencies are now under to show immediate value, this deployment speed is becoming a critical differentiator for us. Plus, with the uncertainty around continuing resolutions and budget cycles that we see in the government agencies, they need solutions that they can deploy quickly when the funding becomes available.
That's exactly right. In fact, David, I'm going to be at a NASA location next week installing two VDURA clusters. And my partner and I in that installation expect to be able to do both of them in the same day.
Absolutely.
So from a pricing model, we're not really doing the old list price license plus support contract approach. Uh, Given the current focus on transparent, value-driven procurement, what's our pricing structure?
So we've completely reimagined pricing for our environment moving into the new world of the V5000. We offer all-inclusive per capacity pricing with no hidden licensing fees and no per seat charges, and support's included from day one. Agencies are going to get that complete cost transparency up front. The price you see is the total cost of ownership. Right now, our pricing is structured with monthly rates, and we offer standard 3, 4, and 5-year support, along with you'll talk about in a later slide, Steve, a 10-year support that we'll be offering. This is going to give agencies the flexibility they need to align with government funding cycles, and also to keep, for example, with that NASA customer you're talking about, they're going to be able to fund and they're going to be able to support their satellite because they know it's going to run for another 5 years. So it's really flexible like that. This directly addresses the DOGE procurement concerns that we're hearing about, and a lot of that is centered around they don't want any more complex licensing structures, right? They want very transparent purchasing requirements. So we here at VDURA, we want to be the easy button for that, and what you see is what you get when we provide a quote.
Awesome.
So one thing I want to talk about a little bit is kind of like use cases and where do we fit in as VDURA, and especially in the federal space. So historically, we've been the go-to solution for traditional HPC workloads. Especially what I see the most is computational fluid dynamics and large-scale simulations. And our customers really love us for those two use cases. I've heard from one large FSI that that reliability that we've talked about that's built into our PanFS file system, he doesn't talk to the other the other competition is when they come knocking, because he couldn't imagine that increase in overhead and the amount of time you'd have to spend managing a traditional system or say a Lustre-based system versus running ours, and the reliability is just there. He can just set it, forget it, and it runs their workloads great. But what we're seeing now is now that we've introduced the V5000 all flash appliance, there's a heavy shift towards AI ML. This evolution is going to perfectly align with some of the initiatives we're seeing coming up in the 2026 budget. One thing that stood out to me is that $24 billion increase in the C2ISR budget. This means that agencies are going to need GPU saturating performance for real-time analysis of intelligence data, threat detection, and sensor fusion from multiple sources. And what's really powerful about our product is these new AI-driven mission requirements. With this, we support that along with traditional HPC, right? So what we're seeing with the V5000 deployments that we're going on here now that we've released is these clusters that they're building are not just running these new AI workloads; they're also being used for traditional HPC as well, and we play well in both categories.
That's great. Thank you, David.
So going back, I want to ask you another few questions here towards the end of this presentation, Steve. One theme that comes up a lot is future-proofing. Infrastructure purchased this year needs to support mission evolution over the next 3 to 5 years. This is what I mentioned with NASA, right? They have a satellite they know is going to be up for the next 5 years. And they're also not only have to support these systems for those 3 to 5 years, they also have to demonstrate measurable efficiency gains. So what is VDURA doing to help federal agencies build for the future?
So there are a couple of things that we're introducing with the V5000 that we've not done before. Starting on the left side of this chart, we've introduced a feature called V-scale flow. As I mentioned before, every one of our storage nodes has some amount of flash storage contained within it. The capacity back nodes then have those HDD JBODs underneath them, which gives them really deep capacity, but nowhere near the performance of the flash that's contained within the storage node that it's supporting. So V-scale flow will allow the system to write first to flash, which means that we can accelerate the applications and then transparently move that data as the flash fills up down to the capacity expansion JBOD below, which means that for the user, it's really transparent. You don't have to manage when to move the data down to hard drives. When you read things back, they will come off the hard drive at very high speeds because reads are always faster than writes. And then again, when we write to that file later on, we will continue to write through the flash down to the HDDs. So that helps with overall managing the workload performance and making sure that we don't have drops in the performance of the system as we're increasing the amount of data that we're stored. We've also seen over the last 5 to 10 years, really, the increase in use of containerization. Kubernetes is a great virtualization technology, different from the traditional VMware kind of virtualization. It's lighter weight, it tends to run a little faster, it's closer to the hardware, and we have a native CSI plugin which will allow you to mount the storage directly to containers. Another thing that we're introducing where we have high security requirements is end-to-end encryption, meaning that we will encrypt data at the client, put it over the wire encrypted, and then write the data to the storage in encrypted form, and it will never be in the clear except at the client. So the storage never sees the data unencrypted. And that's really key for certain kinds of agencies or workloads. And then, David, you talked about this, or you alluded to it before. When we talk about being able to support missions as long as they may be running, we're introducing our 10-year support guarantee. That means that as long as you have some amount of our QLC SSDs and HDDs. We will support those for up to 10 years from the time of installation. This means 24/7 by 365, next business day response for that 10-year life cycle. David?
Thank you, Steve. And that end-to-end encryption example, I think, is a good, just a caveat off of that. When requirements come down from the government onto our federal IT customers, VDURA is very adept at, updating our roadmap and making sure that the product meets those requirements. So I want to come back to this slide again, just to finish it off, and I have a few last two questions for you, Steve. There's one thing you kind of touched on with the power. Not only are we seeing, from DOGE, a lot of these, spending, requirements and showing, ROI and immediate value products, but, the government always has sustainability mandates. So what can you tell us about the footprint, power draw when it comes to long-term cost of ownership?
I'm glad you brought this chart up again, because these three options illustrate very clearly where we can be in terms of both power and the depth of the capacity that we can store within a rack. So again, on the left, you see, an all flash array, 20 petabytes. It's basically a rack and a half. So data center floor space, which is, data centers are getting crowded. They don't have a lot more power that they can bring to play. So the 51 kilowatts here, 52 kilowatts roughly, is a fair amount for that storage. But, if you've got a workload that requires that, by all means, go there. Now, in comparison, you look on the right-hand side, similar 20 petabyte capacity, but now we're just over a full rack. So if you start thinking about how much storage do I expect my program to require over its life, we now have, nearly a full rack to expand into and add more capacity as the needs of the program grow. At the same time, the power draw for that storage has gone down dramatically, nearly half as much. So when you're in a location that doesn't have a lot of power left, or you don't have a lot of floor space to grow into, we can tune what solution you might want based on those requirements as well.
Thank you, Steve. Last big question here before we move on to some quick fire questions. If someone's looking at how to justify this internally, say to a CIO, to a procurement lead, or to an oversight committee focused on efficiency and ROI, what's the big picture value message?
I think there are a couple of value messages here that we can bring. So for the CIO, one, that we're mission focused. We can scale the performance based upon the workloads that we're running. We can also choose a ratio of flash to HDD storage that not only meets or exceeds those mission requirements, but also minimizes the power draw and the physical footprint. From an ROI perspective, we have this 10-year guarantee of support. And then also, storage tends to grow over time, right? Unless you have really great discipline within the program or the agency, data tends to stick around. And sometimes it's because, the programs are using that data over a long period. So we can grow our cluster very granularly by adding single storage nodes at a time to an existing cluster. So you may not buy one at a time. You may buy 2 or 3 or 4 in an annual appropriation, but you can have that level of granularity to determine how much to grow at any given point in time. And those are real values that we think that the leadership of a program or an agency would really value.
Awesome. Thank you, Steve. So we're going to change things up a little bit now. I'm going to ask just a couple of quick fire questions to warm the audience up here. And, the audience, while I'm doing this, feel free to throw your questions into the chat. I've been presenting, so I can't see if there is questions in the chat, but I'll just ask 2 or 3 questions to Steve, and then we'll move over to the Q&A. So First question, can VDURA systems integrate into existing infrastructure, or are we talking a full rip and replace?
Oh, we integrate very easily into existing infrastructure. We will coexist side by side with whatever existing systems you may have. You know, of course, we need to have a network infrastructure that we can plug into, but pretty much anything you might have is something we can use very readily. So no, it's very simple. And even from the client point of view, uh, you can either access our system using S3, NFS, or SMB, or you can install our direct flow clients side by side with other file system clients, and we coexist with those as well.
Great. What kind of onboarding or support do we provide after installation, particularly given the emphasis on minimal operational overhead?
So we do offer training for our clients. We run sort of a larger training program a couple times a year for storage administrators, but we also have a 24/7/365 support portal that is manned by US personnel. So if you submit a question or you have a concern about something that's happening with your storage, you will get a response very quickly from that support team, and they will work with you hand in hand until your question is answered, or whatever problem has occurred can be resolved. And we work with you the entire time.
Great. All right, now I'm going to turn it over to the audience for some Q&A. So, you know, Carosoft team or whoever can, let's see if we have any questions. I'm going to try to pull it up on my screen as well if I can. Oh, looks like we've got a CP polling
We got
question
another
just
polling
popped up.
question.
Yeah, so answer that first, and then we'll go on to that.
It looks like we have a question in the chat. What happens when teams need to scale beyond the initial 1 PB?
So that's a really good question. We can start with relatively small systems. A petabyte is generally the smallest that we tend to go after, simply because of the way our system is structured. But as I mentioned earlier in one of my charts, where David and I were discussing the values statements that we want to bring forward, the idea that we can expand one storage node at a time means that you have very granular changes to the storage environment. Maybe you want to add just that one storage node because that's the budget you have at the moment, or that's because that's only what you need for your next expansion. And that expansion occurs literally by racking and connecting the new storage node. And then when you turn it on, it will look to the rest of the cluster and say, can somebody please tell me what to do next? The storage administrator will see it come up in their display. It will say, please bring this into my cluster, and it will automatically come in and start working. So it's really very seamless, and there's no downtime involved in that process at all. So whether you're growing by one storage node or 4 storage nodes or a dozen storage nodes, it really doesn't matter. It's that simple. What's our next question here? I see one from Charles asking, can you provide use cases within the Department of Defense? Actually, yes, Charles, there are many use cases within DoD. We have a system currently down at the Pentagon that is supporting a classified program. I wish I could tell you what it was they were doing, but I'm not cleared for that program. David also brought up the idea of C2ISR, the idea that you have data ingest coming from some kind of sensor platform or other mechanism where data is coming in, and then you have some kind of processing timeline where that data is enriched and enabled for some other actor to do something with that information that might impact an actual mission in the field, or it could just be something that's going on behind the scenes. And of course, DoD has a very rich HPC research community doing all kinds of workloads in radar cross-section analysis, weather modeling, ocean modeling, computational fluid dynamics, strength of materials analysis, very traditional kinds of things. But we see lots of different workloads in the defense space.
I saw another question came up, and I know it was answered in the chat, but the question was, how does Carahsoft or a customer request a meeting to discuss further? You can reach out to VDURA@Carahsoft.com, and we'll also have our contact details at the end of this as well.
And then,
Another
David,
one?
I see another question from Charles asking if our hardware is approved for use within the DoD. And I don't know the DADMS or DIT PRS. I'm not familiar with those directly.
Be happy to schedule a call at a later date, Charles, and we can discuss this further. We have, as Steve mentioned, we've got clusters in a variety of classified areas. And again, we can't tell what they're doing, and they can usually, the system integrator running them also can't tell us either. So, but happy to entertain that conversation and hear what your needs are around security. It just goes back to what we talked about with the end-to-end encryption going on the roadmap. The moment a customer needs something, we're very responsive and we throw it on the roadmap.
It looks like we have one last question in the chat pod. Why is storage so important for AI and HPC?
Well, the thing about AI and HPC is that you're not computing a single answer or a single set of answers in a data set from a single initial condition. ML models specifically require training on large amounts of data so that they can learn how to take an input and generate an appropriate output. And the data sets for those kinds of model training exercises are generally very, very large. And they have to be very highly curated. You have to have good data that you can start with and then give the model the answer for that particular group of inputs. So the cost of acquiring this data, curating it, going through it, and making sure you can pair with it the kinds of answers you want to see the model generating as a result of that, that amount of effort is very costly. And so having a storage system that not only can feed the GPUs at speed and with the right number of IOPS, but also protect that information and make sure that the data is durable and available becomes ever more important. And I hope that answers the question.
All right. I don't see any more questions. Charles did provide the meaning of those acronyms. So thank you, Charles. Has made
Thank
a note
you,
of that,
Dave.
and
Thank you,
we'll look
Charles.
into
I
that.
appreciate that. Are there any more questions from the audience?
Going once. All right, everyone. So Steve, thanks for all your insight and for breaking this down in a way that is actionable for our federal audience. And for everyone attending today, thank you again for joining us. We'll be following up with some additional materials, including the recording of this. But if you're looking to align your infrastructure with current federal priorities and delivering measurable efficiency gains while supporting mission critical AI workloads, we're here and we're ready to help you make that leap without any of the old traditional trade-offs. So take care, and we hope to connect with you soon.
Thank you all very much.
Thanks again, David and Steve, for presenting. Thank you to all our participants for joining us today. We hope that you found this webcast informative and helpful to you and your organization.